We will now have a closer look at the noisy storage model. This model allows us to achieve security for, in principle, any cryptographic problem in which Alice and Bob don't trust each other. In a nutshell, the noisy storage model assumes that it is difficult to store many qubits without making any errors. Given that no experimental implementation can reliably store more than a handful of qubits right now, this is a technologically well-motivated assumption. It is, however, in principle possible to achieve security even if the adversary could store thousands of qubits. We just need to send more qubits during the protocol. So let's have a look what this model exactly looks like. The model can best be understood by thinking about what a dishonest attacker, the adversary, can or cannot do. We will actually allow the adversary to be computationally all-powerful. He may have a quantum computer which operates perfectly. In fact, we even allow for the operations to be performed instantaneously if this would somehow help the attacker. The adversary can also have an arbitrary quantum storage device before and after the protocol. The only restriction that we will assume that the adversary cannot store qubits perfectly during a waiting time that we will introduce in the protocols. We will talk about storage limitations in more detail in the next video. But for the moment, think that the adversary simply has bounded storage, meaning he can store at most q qubits during the waiting time. So what are these protocols going to look like? Evidently, there's going to be some quantum and possibly also classical communication between Alice and Bob. We will then introduce waiting times. Namely, before proceeding from one step in the protocol to the next, Alice and Bob will wait some agreed upon time delta t. So what does this waiting time give us? What can an adversary do in that waiting time? Remember that before the waiting time, Alice and Bob can communicate. During that time, there are no restrictions at all. In particular, a cheating party can in principle store all quantum communication up to this point. Let me call this the adversary's information before the waiting time. Remember that the adversary has no restrictions before, so in particular he or she can use a powerful quantum computer to encode her information in whatever form he likes. For example, the adversary can use a quantum error correcting code, even if that code would be very hard to realize in practice. As part of such an encoding, the adversary may also perform measurements, resulting in some classical information. The adversary can store an unlimited amount of classical information. However, the only quantum system that the adversary can keep around is placed in the noisy quantum memory. Finally, after the waiting time is over, the adversary can use his quantum computer to recover as much information as possible from the noisy quantum memory and, of course, his unlimited classical memory. For example, he could decode a quantum error correcting code even if that code would actually span all qubits and take a very long time to be decoded. So this is the noisy storage model. We introduce waiting times, and during those waiting times, The adversary can only keep quantum information in a noisy quantum memory.